Example 2 asks us to use the first derivative test to find the relative max and mins of this function given, and this time we have a domain which we'll have to address. We're also going to be talking about intervals of increase and decrease. So, we're focused on the first derivative test as our method. Step 1, we need to find all critical points. We have found that if we know what's happening to the left and the right of a critical point, we know if it's a relative max or a minimum. So I start by taking the given function, x cubed minus 27x, and I take the derivative to get 3x squared minus 27. Now I'm ready to find my stationary points. So I take the derivative 3x squared minus 27, set that equal to 0. Now in this problem, you could add 27 to both sides, divide by 3, and take the square root of both sides, although it'd have to be plus or minus. Most problems, you'll have to factor or use the quadratic formula, so I'm going to go with factoring. Always look to see if you have a GCF, a greatest common factor, and in this case, I can pull a 3 out of every term, which makes the piece I have to factor much easy. It's the sum and difference of a perfect square. So I have 3 times x plus 3 times x minus 3 equals 0. Because it's equal to 0 and I have no more exponents, I can use the zero factor property, so that I can set each term equal to 0. 3 equal to 0, well, that doesn't make sense. There's not a variable. X plus 3 equal to 0 would only happen when x is negative 3, right? I just subtract a 3 to both sides. X minus 3 means x had to be a positive 3 for that parenthesis to equal 0. So I have my stationary numbers. Now I'm ready to find my singular numbers. Again, I take my derivative, 3x squared minus 27. Well, there's no denominator, so this is never undefined, so I have no singular points. Now I have to change the page, and I'm ready for step 2 to actually complete the first derivative test, right? We're using the first derivative test. Even though I just took a derivative, that was not the test. This is the actual first derivative test that's about to happen. I start by making a number line. Now usually it's negative infinity to positive infinity, but because we're told we have the domain of negative 5 to positive 5, my number line goes from negative 5 to positive 5, and I want to list my critical values at the top. We found negative 3 and positive 3 to be our critical values. So I put them in numeric order on my number line and draw lines below them to kind of divide this table up. I need to know what intervals this is created. So the interval from negative 5 to negative 3 is basically to just dump those numbers into interval notation. So remember, this is x1 to x2, not x comma y. That 3 should be negative, and I'm going to catch it and fix it in a second. Now I need to do the next interval, which is between the negative 3 and positive 3. So I just kind of dump those numbers into my interval. They're both round parentheses because only the 5s had square brackets, but we don't really grade you on that. And my last interval is between the 3 and the 5, so I dump those numbers into interval notation. Now I need to find test points from within the interval. So looking at negative 5 to what should be negative 3, I chose a test point of negative 4. If I chose negative 2, that's too small. It's outside of it. We tend to pick whole numbers as test points, but you could have picked negative 3.1, negative 4.999. Looking at negative 3 to 3, there's a lot of whole numbers in between those two ranges. I always pick 0 if it's available. Seems to save me some time doing the math. And in between positive 3 and positive 5, there's only one whole number. If this had been from positive 3 to positive 4 and there's no whole numbers, I tend to pick 3.5 because it's easier. But any number, so long as it's not 3, it's not 5, and it's in between, would be fine. So here's where the first derivative test happens. I am going to test those red numbers in the derivative. Remember, not the function we were given, but the derivative. So when I test negative 4 in the derivative, I'm using the 3x squared minus 27, where x is negative 4, and I end up getting 21. Next, I'm going to test the test point of 0 in the first derivative. You're going to need to indicate that first derivative symbol because this is a problem you'll be writing out. I didn't show you my steps, but if you plug it into the first derivative function, you'll get negative 27. And now I'm ready to test my last point in the first derivative, and I get positive 21. Now we're ready to determine the sign or direction of the interval we're working with. So focused on getting 21 in that first interval, since it's a positive number, I'm in an increasing region of my graph. My derivatives are positive, and so my graph is headed uphill. The next region of my graph had negative 27 as an output. Negative means this portion of the graph is decreasing or headed downhill. And the last interval of my graph had 21 as an output, which is positive, so I'm back to an increasing section of my graph headed uphill. Now I'm ready to determine whether I have maximums or minimums or none at my critical points. So if you remember, the rule is because this graph, the derivative on the left side of my critical number and on the right side of my critical number change signs, I have a relative max at critical number x equals negative 3. Even though I've already used that middle arrow, I'm going to go ahead and focus on the change from positive 3 on the left to positive 3 on the right. And so again, I'm focused that my graph went from downhill to uphill, giving me a U shape, which is a minimum. So positive 3 is a relative minimum. And again, I'd run out of room, so I need to move on to a new page because we're not done with this problem. Step 3, I need to find the coordinates because I need to answer everything as a coordinate. So we said there was a relative maximum at x equals negative 3. So I need to go back to my original function, not the derivative, and f of negative 3 in the x cubed minus 27x function gives me positive 54. This, I never know if the sign is going to be positive or negative, even though it's a relative maximum, because our whole graph could be below the x-axis and all values could be negative. I also had a relative minimum at x equals 3. So again, going back to the original function of x cubed minus 27x, plugging in a positive 3, I get negative 54. I probably should have found the coordinates of the endpoints at this time, but I forgot about it, so you're going to see it in a minute. Because step 4 is always to determining what happens at the endpoints. If your graph didn't have endpoints, if it went from negative infinity to positive infinity, this step would not be necessary. I can only do this really by visually figuring out what's going on. I could write out some rules and I'll talk about it in a second, but I don't want you just memorizing things. I want you to understand the big process. So we have determined at x equals negative 3, we have a relative maximum of 54. So I'm going to go put that on the graph where I'm not worried about it being to scale. I just care I have a point at negative 354, roughly somewhere over there. I also know when x is positive 3, I have a relative minimum at a y value of negative 54. So I'm going to plot that point. Now we just said that the negative 3 was a maximum, so I drew kind of a hill. The positive 3 was a minimum, so I drew a valley or a U shape. I'm going to connect those to give me some sort of graph. I'm not so much worried about the accuracy of how fat, thin, wide this is. I just want the general shape. Now here is where the endpoints come. We said our graph doesn't go on forever to negative infinity. It actually started at negative 5. So everything to the left of negative 5, it's gone. There's nothing there. So my orange graph actually stops at negative 5 to give me a point right here on the graph. And if you remember from the beginning of this section, when I look to the left, I don't see anything. When I look to the right, that purple dot is lower than all orange points to the right, so it's a relative minimum. Same thing happens on the right side. I have an upper bound of positive 5, so my graph stops at positive 5. All that yellow stuff is gone. And so I have an endpoint that is a relative max because it's taller than all orange points to the left of it, because that's all that exists. So now we need to go ahead and find those coordinates, again, going back to the original function, then negative 5 in x cubed minus 27x is going to give me positive 10. And when I do this all over again for positive 5, I happen to get negative 10. A lot of symmetry between these numbers because of this particular problem. That doesn't always happen. I'm ready to answer. Critical points. I know it's a couple pages back. You can still see it on your page. But we had first found that negative 3 was a critical point, and we've already determined the coordinate of negative 3 is a y value of 54. We also said that positive 3 was a critical point with an output of negative 54. This negative 5 and positive 5 are not critical points. They're endpoints, but our stationary points only gave us negative 3 and positive 3, singular, we had none. So for critical points, this is all we have. Even if we have to throw one out, we would still answer it here. Now for interval of increase, if you can see your chart that we had drawn in step 2, you could see that the first interval where we had a value of 21, we said was positive, which equals increasing. You can also see that here, that my graph is headed uphill in between negative 5 and negative 3. So I had an increasing region from negative 5 to negative 3. And visually, or looking at the third column in our table, from x equals 3 to x equals 5, our graph was still headed uphill or increasing. And then visually here, you can see that the downhill section goes from, well, negative 3 to positive 3, or this was the middle column in our graph. And lastly, we need to answer about our relative max and min. And again, looking back at the chart, we had said we had a relative maximum at negative 3, and we're still writing coordinates which are from the original function, so comma 54. But don't forget, we also stated there's an endpoint that's a relative maximum, so I need to list the 5, negative 10 value. Going back to step 2, my second critical number of a 3 was determined to be a minimum, whose y value is 54, but we also have an endpoint that's a relative minimum, which is our final negative 5, comma 10. And we're done with the problem.